Hello, and welcome to section 6.2. So in 6.2, we're going to talk about covalent bonding and molecular compounds. The first section, if you look at your note guide, if you're looking at that, just goes through a bunch of different uh, definitions, okay, and just some terminology that we need to know. I'm going to go through those quickly as you can see them up on the screen. First thing is a molecule, and a molecule is a neutral group of atoms that are held together with covalent bonds. So specifically, ionic substances, which we're going to talk about in 6.3, actually are not molecules. Like NaCl, technically you cannot call a molecule because it's not held together with covalent bonds. Okay. A molecular compound, a chemical compound whose simplest units are molecules. So, again, when we talk about H2O, we're going to talk about that as you can see right here, as being a molecular compound. Okay. This term here is more of a catch-all for any different type of formula, whether it be ionic or covalent. A chemical formula indicates the relative number of atoms of each kind in a chemical compound by using atomic symbols and numerical subscripts. So we are going to be using those symbols that you learned in Chapter 5 and using subscripts to distinguish how many of each atom that we have. Okay. A molecular formula that shows the types and numbers of atoms in a single molecule of a molecular compound. So we can see here, this would be the molecular formula for water, H2O. This would be the molecular formula for ammonia, which is NH3. And this would be the molecular formula for methane, which is CH4. Okay. And lastly, I do want to talk here for a minute about the diatomic molecules. Now, these are elements. Really, any molecule consisting of two atoms is called a diatomic molecule, but specifically these ones that are elements. And in their elemental form, they exist as two atoms bonded together. So as you can see, there are 7 of them. And these 7 you really should know. You should commit them to memory. And they are H2, N2, O2, F2, Cl2, Br2, and I2. So all 4 of the top 4 halogens, okay, F2, Cl2, Br2, and I2. Then going across, you go to N, O, then F, okay, and then don't forget about H2. So when later on, like in chapter 8, when we write, if it says something reacts with oxygen, we have to write that as O2. That's how oxygen exists in its elemental form. Okay, so those are your 7 diatomics. You might want to mark those on your periodic table if you have one, but just make sure that you know those. Okay, couple other things here. We're going to talk about the formation of a covalent bond, as you can see on the screen, and then bond length and bond energy. Those kind of go together. And we're going to use that as one sort of section of 6.2. We're actually going to have 2 videos for 6.2. And then the second video will be based on Lewis structures, which we'll get to drawing next. Okay, so this formation of a covalent bond, this is just showing this specifically is hydrogen to hydrogen. And it shows you really the energy profile of when a hydrogen atom comes together with another hydrogen atom. So we just learned in the last slide that hydrogen does exist as H2 in its natural form. That's its most stable. It does not exist as a single H. So here's what happens when we actually kind of go backwards on this, when 2 independent hydrogen atoms come together to form the molecule. So really in this first step right here, the atoms are as far apart from one another where they're not influencing each other at all until they start to get closer together. So you can see right here, we're at a potential energy of 0. This is an exothermic process. When bonds form, energy is released. Okay, so we're going to look at even as they get closer, okay, closer together here with 2, the energy is starting to decrease. Okay, even before the bond is formed, there's that attraction between the valence electrons and the nuclei of the one hydrogen atom to the other. Okay, then eventually the bond forms, and this is step 3 right here. And there's a couple terms which we're going to get to on next couple of slides called bond length and bond energy. There's a minimum distance between these nuclei that the hydrogen molecule is the most stable at. It just happens to be for H2 or H to H 74 picometers. That's its internuclear distance, or the distance between its nuclei. And this is where it's at its lowest in energy. Okay. In terms of what we call bond energy, it's negative 432, meaning it's going to release 432 kilojoules of energy when that forms. Okay. But as this process of forming, sometimes the nuclei can get too close together, and that causes nuclear repulsion. Okay. Remember, those nuclei, they're very small, they're very dense, and they're positively charged. So they repel each other. So the energy does jump back up here for a little while. And what this bond does, it actually sort of resonates until it reaches that optimum distance right here. Think of rolling like a soccer ball down here. If you roll a soccer ball down here, it would kind of roll here and here and here, and eventually it would settle here at the bottom. And that really is what happens when a covalent bond forms. So these two terms, again, we're going to get to those. The distance here between the nuclei, where it's its lowest in energy, that's called its bond length. And the energy that it releases when that bond forms is called the bond energy. Conversely, bond energy can also be defined as the energy required to break this bond apart. It's the same amount of energy, it's just going in the opposite direction. You would have to put that in. So it would be endothermic. So in chemistry, we always use sort of the terminology of when bonds form, energy is released and it's exothermic. When bonds are broken, it is endothermic and energy has to be absorbed. Okay, so here's our two terms, bond length. Bond length is the distance between two bonded atoms. Okay, it's where their potential energy is at its minimum, where it's its most stable. It is a length, so it is measured in a meter value. For most molecules, it's measured in picometers. And remember, picometers is a trillionth of a meter. Okay, and then here's our other term, this bond energy. Bond energy, that's the energy required to break a bond and form neutral isolated atoms. Again, the other way you can think about that, it's the energy released when two isolated neutral atoms come together. It's the same amount of energy, just going in different directions. Okay, so if you're going to break them up, you have to provide so much energy. When they form, they're going to release so much energy. Okay. So lastly, before we get to drawing Lewis structures, and like I said, you're going to have two videos to sort of watch during this time. I just want to talk real quick about the octet rule. And this kind of goes back to chapter 4 and electron configurations. And really when we form compounds, when these atoms get more stable, what they do by losing, gaining, or sharing, and specifically we're going to talk about sharing electrons with section 6.2. So they have an octet of electrons in their highest energy level, which is 8. So 8 electrons is going to be very important. We're also going to talk about the duet rule, which for hydrogen is 2. Hydrogen always needs to find one other electron to bond to. But these are rules that will sort of guide us through not only writing those electron configurations, but drawing Lewis structures. And remember, with octets, when we looked at the noble gases, and one of the reasons we could use noble gas notation was because they were already stable. They already had 8. They were all S2p6s with 2 valence electrons in the S subshell and 6 in the p subshell, gave us 8 total.